Welcome to the fourth tutorial in the ReaCoMa tutorial series. In this tutorial, we'll look at several of the slicing algorithms and how they can be applied to different segmentation tasks. The point of this tutorial isn't to enumerate all the parameters of each algorithm and to explain them to you. In fact, the command line interface download comes with a HTML file that can do that for me. The point of this tutorial is to guide you through some segmentation scenarios and to demonstrate how you might deal with them using the ReaCoMa tools. A quick reminder, slicing is the process of segmenting or cutting up audio. You might already be familiar with the splitting tool that Reaper natively implements, which is a kind of slicer. Some of the ReaCoMa algorithms work similar to the built-in slicer in Reaper, while some use some more recent and novel techniques. What I really want you to take away from this tutorial is that each slicer is good at different things, and there isn't one algorithm that can work for all scenarios. That's why having several algorithms at your fingertips can be really powerful. There are several slicing algorithms that can be divided into two archetypes. Ones that operate on amplitude and in the time domain, and those that operate on spectral frames in the frequency domain. The important fundamental to remember is that regardless of the underlying implementation, all slicers are essentially algorithms that try to identify time points where a certain threshold of change has been exceeded. Amplitude-based slicers are more appropriate for sounds where differences in volume and amplitude align well with the way that we intuitively perceive segments. Slicers that operate on spectrums or spectra will work better for audio where differences in tone color or timbre indicate the start and end of logical segments. No class of slicer is going to be a one-size-fits-all approach, so it's good to have access to a variety of algorithms to help you make decisions that are appropriate for the specific context. I'll start by presenting some scenarios and then demonstrate how you might approach a solution using different slicers. Segmenting percussive material is well suited to the family of amplitude-based slicers. The morphology and sonic behavior of this sample is also a type that could be found outside of the instrumental context. Ultimately, this sound presents a lot of changes in amplitude, and this can be latched onto by a few of the algorithms available in the toolbox. The amp slice algorithm works by following changes in the amplitude of the audio. The algorithm is a bit more clever than simply tracking the ups and downs of volume though, and uses two envelope followers to track changes. An envelope follower is an algorithm that attempts to follow the contour of a signal. It does this by sliding along the audio data, calculating the amplitude in decibels, by collecting up groups of samples along the way. What we end up with is a smoother but less detailed representation of the signal, which is useful for identifying changes. The curve that the envelope follower produces can be quite similar to how we perceive the sound, although not always. One of the envelope followers in Fluid Amp Slice calculates the amplitude using a small window of audio samples. Fast and immediate changes are captured with this envelope follower, while the other follower is less sensitive to those immediate and fast changes, and tries to track the general changes over a much slower and longer time period. The magic of this algorithm is that it uses both envelopes to infer onsets by looking at the relative difference between the two envelopes. The general thinking is that we perceive an onset when an immediate change is exceptional compared to what we've heard over a longer period of time. Something might be loud in absolute terms, but we won't perceive it as an onset if everything around it is relatively loud. Let's dive in and start tweaking the algorithm. Here I'm going to slice with the default settings except for the thresholds. For these settings, I'm going to set the off threshold to 0 dB and the on threshold to 12 dB. This means that the fast envelope has to exceed the slow envelope by 12 dB for an onset to occur. Notice how the slicing is way too aggressive, and has even produced segmentations within parts of digital silence. There is also some incredibly tight but granular slices that are almost too small to hear or reasonably extract for any other purpose. To remedy the issues of my previous slicing attempt, I'll only change the on threshold by 12 dB. This means that the fast envelope follower will have to exceed the slow envelope follower by a much bigger margin than before. Just pushing the two thresholds further apart made the slicing more aligned with my perception of the sound's changes. We could even go further and start to alter the time windows that both the fast and slow algorithms work over. By default, the fast envelope follower works sample by sample, while the slow envelope follower takes blocks of 100 samples to average the amplitude over. I'm going to increase the fast envelope to 100 samples and the slow envelope to 1000 samples. What we should see is that all the fast and detailed changes are no longer captured and only grosser changes produce segmentations. Another approach might be to use the amp gate slicer. It's very similar to the amp slice slicer, but it doesn't work on relative thresholds. Instead, amp gate requires you to set absolute thresholds, but this gives you the power to determine when a segment of audio can be considered on or off, rather than just having a time point at which some change occurred. This can be great for carving out quiet sounds from a sample, perhaps to edit them away, or hone in on them for creative use. The silent portions of this track are easily carved away and muted, leaving the most active parts remaining. The mute parameter lets you define whether the muting behavior is enabled or not. Final, less straightforward approach might be to use the transient slicer. This algorithm is especially powerful if the start of an onset is where there is significant and sharp change. This algorithm uses a special approach that focuses on trying to identify points of change in relation to audio samples that surround a given time point. We have to imagine that the transient slicer can look forward and backward into time, simultaneously judging whether a specific sample or group of samples is an outlier with those that surround it. I would recommend an excellent article on the ReaCoMa Knowledge Exchange, which I'll provide a link to in the description and in the video. Slicing textual material can be really difficult, and most tools don't provide ways for us to chop up audio based on changes in the timbre or tone colour of the sound. ReaCoMa has some great slicing algorithms for doing this, such as Novelty slice or Onset slice. The concept of novelty is a multi-pronged approach to segmentation. While algorithms like AmpSlice or AmpGate track changes in amplitude, Novelty slice creates its own novelty curve. This curve can actually be created from several sources of information and isn't restricted to looking at the amplitude of a signal. For example, in the ReaCoMa implementation of this algorithm, you can use the spectrum of a signal, the MFCCs of a signal, the pitch, or the loudness. This gives you some power to slice based on features that are a little more abstract, but perhaps perceptually relevant to the segmentation task. The basic gist of this algorithm is that it puts a sliding window over the audio. Starting at the beginning of our sound file, we take some measurement of tiny chunks of samples inside that window using the spectrum, MFCC, pitch, or loudness. That's up to you. The interesting part is that inside of each bigger window, each of these little chunks is compared to the other chunks, and so it builds a big matrix of similarity between different points in time. By doing this, the algorithm is able to look at a point in time and gauge how different that point in time is compared to what has come before it and what might come after it. We have control over the size of the window, or in novelty speak, the kernel, which means we can start to think about slicing in the long term and not just on the immediate changes. If you want to learn more about the novelty curve or the novelty algorithm in general, I'd suggest looking at the seminal paper which I've linked in the description. Because we can construct novelty from several different audio descriptors, it's quite powerful at latching onto changes in signals that are both well-defined or a bit more murky. With some heavily pitched material, I'm going to approach segmenting it by running the novelty slice algorithm on the spectrum. The slices that were produced with the kernel size of 3 aligned well with the new notes most of the time, giving me some control to rearrange the melody. Experimenting with the kernel size can let you explore segmentations that are less sensitive to short scale changes and might be more relevant to the medium or long-term structure of a sound. By just changing the kernel size from 3 to 7 and keeping the threshold the same, the segments start to encompass a whole lot more material while still seeming musically sensible. Another scenario I'll propose is a harsh digital sound that is mostly consistent in amplitude with some minor variations. The biggest audible difference in time with this sound is the pitch and the roughness of the texture. Using novelty on the MFCC of this signal can make it easy to produce segments when there is significant textural change. As a note of interest, all of the slicers work on reversed and time-stretched samples too. You'll have to remember that the algorithms work on the raw audio though, and they don't operate on the post-FX samples unless you first render them to a new take or item. This brings us to the end of the slicing tutorial. There is still a lot I haven't covered, such as each slicer's parameters, or the onset slice algorithm at all. The best way to learn about these tools though is to try them out for yourself and to start finding what parts of them are more mysterious. Unfortunately, the world of segmentation is complex, and a lot of the answers to questions you might have are, it depends. Because of this, I'd encourage you to ask questions and get involved in the discourse when you get stuck, as the community has a lot to offer in this regard from both a technical or artistic point of view. In the next tutorial, we'll be looking at the various layers algorithms in a similar fashion.